All right. Today's lecture will be on pH step titration calculations. We've examined titrations at this point during the school year. Titration is mixing an acid or a base using a burette to try and achieve the equivalence point where the moles of hydrogen ion equal the moles of hydroxide. A step titration is a slight variation on a normal titration where you add the base or acid that is contained in the burette in a specific amount. So rather than adding a drop and waiting for the pH to stabilize and adding another drop and waiting for the pH to stabilize, we're going to add 5 milliliters of base or 10 milliliters of base and determine what the pH reading is, or calculate what the pH reading is at that moment after all of that volume of base has been added. So we have the 6 steps currently displayed on the screen that we will follow for this process. We'll go ahead and move over to our practice problem that we have. We're going to do 60 milliliters of 0.1 molar nitric acid by 3 molar lithium hydroxide. We want to know what the pH of the solution is after the following volumes of lithium hydroxide have been added. So first step, we've got to write 3 equations. We're dealing with a strong acid and a strong base, so we need to write those ionization equations. And we also need to write the acid-base neutralization reaction. We'll start with that one. We have nitric acid, HNO3, is going to react with lithium hydroxide to produce water and lithium nitrate. We then have a strong acid and a strong base. Our strong acid will ionize 100% to produce hydrogen ions and nitrate ions. And then our third and final equation will be the strong base dissociation of lithium hydroxide. It's important to have all 3 of these so that you know these molar ratios that you will ultimately use in the problem. Now, part A, we have 0 milliliters of base added. In other words, we want to just simply calculate what the concentration is of our acid. We have 0.1 molar HNO3. Since it's a strong acid, we can do a molar ratio. We know for every 1 mole of the molecular acid, we produce 1 mole of the hydrogen ions. So that's our ratio, 1 mole of HNO3 to 1 mole of H positive. That gives me 0.100 molar of H positive. Then the second part of this, to calculate the pH, we're going to do the negative log of the hydrogen ions. And so we're going to have the negative log of 0.100, and that pH is going to be 1. Now, be careful at this step. You've got 3 significant figures here, so your answer needs to show 3 significant figures. It is not sufficient just to simply write the whole number 1. Make sure you are taking into account all the significant figures that you have. So part A is a little bit different because we haven't added any base. Part B is where we will have added our first amount of base. So at this point, we go back to our steps we have on the previous slide. We've already done step 1. Chemical reactions are the same for all the different parts of the problem. So now we need to do part 2 and part 3. Solve for moles of hydrogen and solve for moles of hydroxide. We're going to have 2 monorails. The first monorail is going to start with the 60 milliliters of HNO3. And the second monorail will start with the 10 milliliters of lithium hydroxide. Ultimately, we're trying to get moles of hydrogen from the top monorail and moles of hydroxide from the bottom monorail. Let's focus on the top one first. First off, we need to get ourselves onto the mole map. So we'll convert from milliliters to liters since the bottom spot on the mole map is measured in liters. Then we will move from the bottom of the mole map into the center by multiplying by the concentration of 0.100 moles per liter of HNO3. And then lastly, we'll use the balanced chemical equation that we wrote earlier, that for every 1 mole of HNO3, we are going to produce 1 mole of hydrogen ions. unit-wise, everything cancels out except for the last unit, moles of hydrogen ion, and we get a calculated answer of 0.00600 moles of hydrogen ion. So that's step 2 of the steps that we did on the previous slide there. Now we'll do step 3. We got a very similar calculation, except we want to get to moles of hydroxide. Same process, we're going to have 1,000 milliliters in 1 liter, then multiply by the concentration. We have 0.300 moles per liter of the lithium hydroxide. Then, using the balanced chemical equation from above, for every 1 mole of lithium hydroxide, we will produce 1 mole of hydroxide ions. And that number is 0.00300 moles of hydroxide. Just like the excess problems, we recognize that we have more moles of hydrogen ion than hydroxide, so we're still going to have a pH reading below 7. We have an excess of hydrogen ions in our solution. We also recognize that hydrogen ions combine together with hydroxide ions in a 1-to-1 ratio to form water. So because of that 1-to-1 ratio in that net ionic equation that we have up on the board right here, we can just simply subtract these two values from one another to figure out the excess amount. 0.0600 moles of hydrogen ion minus 0.00300 moles of hydroxide. We get 0.00300 moles of H positive in excess. That is step 4 right there. Now we're ready to do step 5. We're going to take the excess moles and divide it by the total volume. The total volume are these two numbers that we started with, added together and converted into liters. So we have 60 milliliters of acid plus 10 milliliters of base gives me 70 milliliters of solution, and then I'm going to convert that 1,000 milliliters in 1 liter, and that's going to give me an answer of 0.0700 liters. Take that number and divide these two by one another. So I have 0.00300 moles of hydrogen ion divided by 0.0700 liters. And that gives me a concentration of 0.0429 molar hydrogen ions. Last step, step 6 of that step, the process that was on the previous slide. We're going to calculate the pH. So we're going to do the negative log of 0.0429. Again, watch your sig figs here. You should have 3 sig figs. So you've got 1.370 as your value there. All right, that is part B. We've got one more part to this problem. We can see listed down below here. We now have part C. First thing that you want to recognize is that the moles of hydrogen from part B does not change. This value right here, we don't add more acid as the problem continues on. Therefore, that mole value will not change. So, first thing I do is recognize from part B, we've got 0.00600 moles of hydrogen ion still. The part that's new is the fact that we've now added a total of 20 milliliters of the base. So we will have to do a monorail that is very similar to the one that we previously just did, this one right here, except this starting amount will be different. Otherwise, the 3 steps are the same. We're going to convert from milliliters to liters. Then we're going to multiply by that concentration, 0.300 moles per liter of the lithium hydroxide. And then lastly, we're going to have for every 1 mole of lithium hydroxide, we're going to have 1 mole of hydroxide. And we get 0.00600 moles of OH. Just like we did in the previous problem, we are now going to do 0.00600 moles of H positive minus 0.00600 moles of OH negative, and that gives me 0 moles in excess. In other words, the moles of hydrogen ion equal the moles of hydroxide. We have achieved our equivalence point. When you have a strong acid and a strong base, the equivalence point is at a pH of 7. If I were to give you, say, part D, and we continue to add base, you need to recognize that then you're going to have an excess of hydroxide rather than hydrogen ions, so that when you calculate that, you're going to have an excess concentration of your hydroxides. Please don't forget that when you take the negative log of that, you're solving for POH rather than pH, and you have to do a last step of subtracting from 14.